Welcome back. So, with the lectures so far, we've shown how you can take algorithms and implement the neurons, and then I've argued that in the future, we should be able to have hardware that will let us do very large-scale simulations. At the moment, we are limited by what we can do on GPUs, but even that should be enough for a fair bit of research. But if we're particularly interested in human cognition, well, then we want to build up something like cognitive level models. So let's take a look at what sort of things we will need for that. And given the components we have so far, what sorts of basic cognitive systems can we build? Sensory aspects are somewhat straightforward. There's a lot of work in how neural networks can be applied to vision. And indeed, since all of the stuff that we're talking about here, if you don't have a more detailed theory about how exactly what the visual processing is, then hey, use a standard deep neural network to train up a vision system. If you do have detailed theory, then we can sort of constrain that in a more detailed way, but that should be straightforward. For the motor side of things, it turns out that most of motor control and control theory, optical control stuff, a lot of that is already pitched in terms of differential equations. So when we've gone ahead and tried to model motor systems, mostly we can just get away with just grabbing the existing motor control literature and try implementing those things. A lot of details in terms of how to modify that to actually make it more biologically realistic, but that's sort of the type of direction that we would go. For memory, which is another important aspect in your brain, we've established that one particular dynamical system that we can implement pretty easily is an integrator, and that seems to be an interesting basis for a lot of work on memory itself. But then we still have sort of questions also about, well, okay, we still need to sort of coordinate these things and how to get them to work together. That'll be the topic of a future lecture. But I just want to sort of give a quick picture that, yes, you can, within Nengo, do these sorts of things that I was just saying. So here's a vision system. This is just a standard 4-layer deep neural network doing MNIST, which is the standard digit recognition system. Go through a bunch of neurons, pick the output, and have that output. What we're plotting for the output, this is a type of graph that we're going to see a lot of. What we're saying is that the output layer, there's some pattern that means each of these numbers. So there's some ideal pattern for 2, some ideal patterns for 0, and we're just indicating the similarity between that neural activity and the actual neural activity that's produced by the network. The reason that we're doing something like that is we're not going to be doing something like applying a softmax function or similar sort of make a decision or sort of classification type thing on the end of one of these networks, because the idea of taking a network like this and combining it into other neurons means that you want to be able to just use the output of this network to connect to other groups of neurons directly. You don't want to add in your own extra computation that we would then also have to figure out how neurons would compute. Anyway, so again, that graph that we're seeing down there on the right is the similarity measure. So how similar is the output right now to the ideal output for these things? And then on the left is just a sort of a visual depiction of that same thing. So just the size of the text relates to how close the output pattern is to the ideal pattern. But anyway, you can take visual models and just apply them and combine them in with Nengo models because, hey, it's all neural networks. I also mentioned motor control. Yes, you can. So here's an example of taking operational space control and dynamic motor primitives. And basically what you're doing is you are having the system calculate, well, how much force should I apply at each of those joints in order to follow some particular path, right? And you can just take that, turn it into math, turn it into differential equations, and have it go do what you want. But as I was saying, we need more to do cognition. We need to represent, how in the world is something like this going to represent symbols? How are we going to even manipulate symbol structures? And I think this is sort of like the really big sort of question that a lot of people hit at this point is, fine, this is great for like doing like math, and okay, maybe we can see how this works for motor control, but symbols are different. How in the world do you do something like symbols when all you have is vectors? And then on top of that, we have this question about, well, what about cognitive control? How can we change tasks? How do we do different things at different times? Because we can't like rewire the brain. As I said, we will be looking at the symbols aspect right now. Future lecture, we'll talk about the cognitive control. First, I want to sort of demonstrate, yes, it is totally possible. So here is the an addition by counting example. So all of these are spawn. We showed it a 6, we showed it a 2, it wrote an 8. So that looks pretty symbolic to me. So we asked to do 6 plus 2, we figured out it was 8. Earlier we saw a 4 plus 3 example, we figured out it was 7. That's all good. Other sorts of things we can do. We can also, here we're going to present it a sequence of numbers, 8, 6, 9, 4, 7. And then we're going to ask it, where is the 6? And it says it's in position 2. That looks like a pretty symbolic sort of operation. Other sorts of tasks that spawn can do. We're going to give it a sequence, 9, 4, 7, 3, 0. And then we're going to ask it, what is at position 5? It's going to say there's a 0. Okay. Fairly symbolic task. How did we get spawn to do this? This is just a large neural network. And importantly, the way that we're building these things up out of algorithms and components, there's nothing like the standard neural network approach of give it a whole bunch of examples and train it up. There's no deep learning. There's no here's a whole bunch of examples of this task. It's never seen this list before. It's never seen this particular task. All that's happened is we've taken these tasks and broke it down into particular components, each of which we can instantiate. You combine all the components together and it can do the whole thing. And importantly, it was the same model that did all of these tasks. It's able to change the task just based on what task it's doing, just based on the visual input. The last type of task that I'm going to show, just to sort of drive home that this symbolic type stuff can be fairly complicated. This is an example of a task that's based on the Raven's progressive matrices. We're showing it a pattern. The pattern is being shown one symbol at a time because spawn just has a single eye. On the left, we're showing the pattern so that we can see it. And spawn is supposed to figure out what comes next. And it does this pretty well. So it filled in 555, which is sort of the logical next thing there. How in the world did it do that? That's a pretty complicated symbolic logic sort of task. And we'll do one more example of it. And again, like the key question here is, how are we going to take this task, turn it into something that looks like vectors and functions on vectors and differential equations? The only thing that's being presented is these symbols. We can assume that the vision system sort of works. We can assume the motor system sort of works. What's going on inside? There we go. It also was able to do that pattern as well. How? How are we going to do symbol manipulation? If we just decided to take the sort of standard algorithms of symbolic logic, as I said in the previous section of this lecture, you could just implement a Turing machine. That's just going to be ridiculously slow and use tons and tons and tons of neurons and be nowhere close to the right speed sort of process. And not look anything like the human brain. So how are we going to do this? Because those sorts of algorithms, if we just go ahead and try to approximate them with like single groups of neurons, they're not going to look like those algorithms don't look like smooth functions of continuous variables. They're definitely not low-degree polynomials. How do we do symbol-like operations with vectors and smooth functions? So this is going to lead us to the concept of what we're going to call a semantic pointer. The general concept that we're starting with is pretty general, like has been used in lots and lots of different places, well before we started using it. The core idea is going to be something that we're going to start with the idea that, fine, there's vectors for each basic concept. So red has a vector, there's a vector for blue, there's a vector for dog, there's a vector for house. And we can either randomly choose them, or there's also tons of methods out there in the literature for how to generate vectors such that you've got some sort of semantic similarity there. Word2vec might be a common one that people might have heard of. But the idea is if you have a vector for each symbol, you probably want your vector for red to be kind of similar to your vector for pink, as an example. And then the core idea is going to be that, okay, well, if you have something like that, and if you have a way to store vectors, which we do because we have that integrator that we defined before, then we should be able to store a set of symbols. Okay. And then we might be able to even ask questions like, okay, well, how many can we store given a certain number of neurons? Right? I'm also going to say, so as we get into this sort of symbol representation stuff, everything we've said so far in the course about just how do you implement algorithms using neurons, that's on pretty strong theoretical grounds. It's sort of like, okay, given what we know, given these sorts of assumptions about what neurons are, this is the class of things that neurons are good at. Okay, and that we've, the derivations and processes that we talked about in the last two lectures, I think really focus on that. This is provably the right thing to do with neurons. As we're getting into this vector representation stuff, we're on shakier ground. So what I'm presenting here about how to reproduce symbol manipulations using neurons, the strongest argument I can make for it is I can't come up with a better way. Okay, so there's no proof that this is the best way, but we've had great difficulty coming up with other ways. And also, if you're looking for other resources, the stuff in the previous lectures was in that book, Neural Engineering. The stuff in this lectures and going forward is in this other book we got a picture of here at the bottom called How to Build a Brain. That's more sort of saying, well, if we're constrained by the stuff in that first book, the first book lays out, here's what neurons are good at in terms of implementing algorithms. And this is more sort of, well, if we have those constraints, what's the best job we can do of implementing something like a cognitive algorithm? And here's our best guess for what those components are like. So that's sort of the transition point that we're having at this point. Now we're getting up to higher level cognition. We're maybe a little bit more speculative. In any case, this idea of vectors as ways of representing symbols, just each symbol has its own vector, at least there's a relatively wide tradition of doing something like that. So let's see that in Nengo. Whoops, whoa, there we are. So if you run Nengo and you open a file, you go to built-in examples and tutorial. One of the ones down here is called SPA. So SPA, it's semantic pointer architecture. That's our first of the demos that start getting into this, our best guess of how to do high-level cognition stuff. Okay. It introduces a few new components. The documentation sort of describes these components. Importantly, all these components are built out of the things you've already seen before. Right? So it creates these blocks. If you want to, you can click on these blocks, and yeah, there's things inside them that are, it's all built out of the things that you've seen already. Okay. And all we're doing here is we're adding in some sort of user interface stuff in order to help us represent vectors. Okay, what do I mean by that? So what this particular example has got is I've got one group of neurons over here that I can feed in that I can represent a vector, and I've got another group of neurons over here that represents a vector, and it has that recurrent connection that allows this one over on the right here to be a memory. So let's say I want to feed a vector into this. All right. If I right-click on this, double-click on this, double-click on this, I'm going to right-click on this output and plot the value. Right. And I can right-click on this input and plot the slider. This is set up to be a 32-dimensional vector. Okay. And if I press play right now, what I've got is I've got a group of neurons that can represent a 32-dimensional vector. We're just focusing on this one on the left right now. Maybe I'll put this up here. There we are. And so if I want to say put in this vector, all right, yay, that group of neurons is now representing that vector. Right? It's got some neural activity. That neural activity can be decoded to be that vector. There's 32 lines here. This is exactly the same as the example we've seen before, just scaled up to 32 dimensions. Now, this is a pretty useless interface, right? Using these sliders in that graph, because how am I going to remember what if I decided that this particular pattern means dog and this particular pattern here means cat, how in the world am I going to remember all of that, right? And how am I going to be able to look at this top graph and figure out, is that close to dog or is that close to cat? It's just not helpful. So I'm going to make these go away. And instead, there's this new type of plot called the semantic pointer cloud. In this example, we've already got one created for us. And what we're going to do here is I can take this plot here. Actually, let me, before I go any farther, let's pull up that output plot again, just to sort of see things. All right, so there's nothing being represented in here, or it's all right, not nothing being represented. The vector 0, 0, 0, 0, 0, 0, 0 is being represented in these group of neurons right now. That's what we can see based on this output. If I take the semantic pointer cloud plot and I right-click on it and I say set value, and I say dog, it randomly generates a vector that means dog and feeds that into that group of neurons, because it has no idea what a dog is. If you want to, if you have another way of generating vectors, you can build that in, or you can set that up. The default is just every time you get a new vector, it randomly generates a new one. Okay. Let's ignore this memory one over here for now. I'm going to remove that. If we then go to this vision and we set it to cat, cool, that's a new vector. All right. And we've got a new representation there. If I set it back to dog, it goes back to the thing it was before. Okay, it's the same pattern as before. Importantly, since these are all vectors, I can do math on them. So I could also say, well, set the vector to dog plus cat. That's just another vector. Okay. Now, why is this display showing this way? That's because this is the sort of plot that I showed earlier, and so that's indicating that the vector that's currently being represented is kind of close to dog and also kind of close to cat. By kind of close, I mean if you do the dot product between the vectors, you get a large number. So given that sort of display, this display on the right starts being really, really useless. It's just, staring at those lines doesn't really help much. So most of the time I will just remove that. One other graph that can be useful, if I right click here, there's both the semantic pointer cloud, but there's also the semantic pointer plot. So those are just two different ways of representing the same thing. Okay, I'm feeding in, no, let's feed in dog. Okay, so the vector that's currently being represented here is kind of close to dog, not very close to cat. Okay, if I feed in, I don't know, house. There we go, it's a new vector. It's kind of close to house, not very close to the other ones. If I feed in dog plus cat, right, I get a vector that's pretty close to both of those. And of course I could also do dog plus 0.8 cat. Right. They're all just different vectors. Okay, so that's just sort of establishing these graphs and establishing this sort of new way of, instead of moving, the only thing I'm doing here is instead of moving sliders around, I'm able to just type something and then the user interface takes care of doing the equivalent of making sliders. And instead of looking at that output as just here's 32 lines, the interesting thing that I want for the output is, well, how similar is that output to all the different things that I know? Okay. So we have these graphs. Let's actually make this thing actually start to represent something. I'm going to go back to set this to dog. Okay. This memory over here, I said that it's the same as what we've defined before. It's just a group of neurons, represents a 32-dimensional vector in this case, and it's set up as an integrator. So that should, if I now pull up a semantic pointer cloud, I should see this. So I'm feeding in dog into my vision. My memory now has dog in it, or a vector that is very close to dog. And if I take away my vision, because my memory is an integrator, it still is dog. And you'll notice it drifts a little bit, right? It jitters a little bit, it changes a little bit. That is exactly what we saw with the fact that this integrator is not perfect, right? The neurons are attempting to approximate an integrator. And just like, say, with the critter example, where its knowledge about its position wasn't perfect, would drift a little bit. Those sorts of same effects are going to happen here, right? And which is actually kind of nifty, because then you can start doing things like, oh, hey, well, how long is it going to take for it to forget this? Okay? And that's going to be a function of how many different terms there are in the language, how many different words there are that it can refer to, and how many neurons we're using. But I can also do things like feed in cat, and now the memory starts drifting closer and closer and closer to cat. If I feed that in for long enough, it can push out the dog memory. Right. But I can also do something like, oh, let's feed in rat, right? And then I can, take something away, and now we've got something that's representing kind of close to cat and kind of close to rat. Okay. Again, it's not like there's two separate vectors that are being represented, it's just one vector, but that vector is kind of close to cat and kind of close to rat. Okay. And again, you can see it sort of drifting. Right? And in general, it's going to behave better with more neurons and more dimensions. Okay, so that's the basic idea for vectors being represented in this system. Okay. We can then go ahead and start exploring such a system. All right, so that's sort of the straightforward way of taking that idea of, concepts are vectors. How well can that system work? So one thing that falls out pretty quickly is more dimensions. If you add more dimensions, so that was a 32-dimensional vector. If you add more dimensions, you get better capacity. Capacity in terms of how many different terms you can store for a reasonable, we did like 30 seconds or for whatever sort of time you want. More dimensions, of course, is going to require larger neuron groups. So then you've got an interesting question about, well, how far is it reasonable to scale that up? Would it be okay to scale that up to 1 billion dimensions? And one way to answer that is to sort of say, well, when we go ahead and make those connections, when we make that system, there's basically, when you do that recurrent connection, you tend to have something like an all-to-all connection between the neurons, right? So you've got this recurrent group of neurons where pretty much every neuron is connected to every other neuron, or a reasonable proportion thereof. And so that starts asking the question of, well, how big a group of neurons do you actually see in human cortex that's sort of recurrently connected, or sort of they're all similarly connected? And the particular experiment that is sometimes done in that is you inject something into one neuron and see how many other neurons, or inject something into some small group of neurons, and then you see how many other neurons does that immediately affect. And the numbers there somewhere on the order of 40,000, maybe 100,000, something like that is the sort of range of things that if I needed to get a group of neurons much larger than that, I would start being worried about the biological plausibility. So that gives us sort of a number of somewhere around 40,000 neurons to sort of represent one, that could represent a vector. That's, I guess, sort of the sort of the upper end. Ballparkish. I wouldn't want to go to 1 million is basically all I'm really trying to say there. But you could take all those neurons and have them, that's how many neurons you have, but there's a separate question about how many dimensions do you want. Right? So you could do all 40,000 neurons just represent a one-dimensional value extremely well. Or you could have them represent a 40,000 dimensional vector, but really, really badly, each one, right? So where's this trade-off? And turns out there's a reasonable sweet spot, somewhere around 700 dimensions, that seems to be the upper end of what I would want to argue you could find in humans, right? So and it turns out the question is, if you have a neural ensemble of that size, is that enough to do human vocabulary? Does this approach that I'm describing here scale to adult humans? And the answer is yes. So estimates is something like 100,000 concepts in adult humans. So we can test that by just simply generating 100,000 random vectors, feed one of them into the model, wait a couple seconds, take the vector that is coming out of that model and say, okay, well, which one is it closest to? Or, we can feed in 8 concepts at the same time, and then see does the output is the output stable? So can we, so the output is never going to be exactly the same as the input. The key question is the output closer to the correct, the input that you gave than any other thing? And yes. So that works great. Scales up to human size vocabulary like that, no problem at all. But key problem, people do more than just store concepts. People relate concepps together, and this is sort of the core challenge to any sort of neural representation of concepts. Indeed, people have sort of argued that this is the fundamental thing that you need to explain if you're going to be trying to do something about neurals and neural systems and symbol systems. And it's referred to as the binding problem. And here's the classic problem. Okay, how do you store red circle and blue triangle? All right. Stuff I showed there. Okay, yeah, you could represent a symbol for red. You can have a vector for red. You can have a vector for circle, a vector for blue, and a vector for triangle. If I want to represent red circle, cool. I just take the vector for red and the vector for circle, and I add them together, and that's the vector for red circle. But I can't do that for that whole thing. I can't just say red plus circle plus blue plus triangle and say, okay, that's the vector for red circle and blue triangle. The reason is that you can't distinguish red plus circle plus blue plus triangle from red plus triangle plus blue plus circle. Right? It's the That's the same math. So that's why it's called the binding problem. We need some way of indicating that circle is associated with red and triangle is associated with blue. Okay. So we need some way of combining these concepts. And this is, again, not a new problem. Lots of people have studied this before. And the general approaches that people have taken is to say, all right, there's more math than just addition. Let's pick some other math, and we'll write it as this star with a circle around it, and say, okay, there's some other mathematical operation that we're going to use there. And if you do that, then you get a new vector that now represents red circle and blue triangle. And that's just a new vector that can be stored. Okay. And that should all work fine. Importantly, I mean, as with all of these things, because we've built our group of neurons to represent any vector, of course it can also represent this vector, even if it's never seen that particular combination before. So it means it can represent novel combinations of things. There's of course going to be some sort of question about how much information can you combine together, and there's certainly some lost information there, because we're taking 4 vectors and combining them down into one vector, and all those vectors are the same length, so there's going to be something lost. And then the question is, how much can we recover? And so basically what we're going to say is, okay, this operation that we've defined for binding, we're going to need some sort of inverse operation as well. Okay. And so what we're going to want to be able to do is something like this sort of math, where if I have red circle and blue triangle, and I want to know what circle was bound to, but the only thing I have is the result of doing that math. So red circle plus blue triangle, I have some result there. I want to be able to take that result and do some more math on it, and here we're writing it as bind with the inverse of circle. And as long as that inverse is sort of well behaved, as long as that inverse behaves like a mathematical inverse is supposed to, and as long as this, whatever this symbol is, this binding operation behaves kind of like multiplication, then we should be able to do math like this. We should be able to say, all right, so red circle plus blue triangle, and we combine it with the inverse of circle. And if we go and expand out those parentheses, this should be red combined with circle combined with the inverse of circle. Those should cancel. And then these should do something else. So that's going to give us the vector for red plus something else. And the vector for red plus something else is still going to have a pretty big dot product with red. Okay, and so red plus something should be similar to red, as long as whatever this binding operation is doing is giving some result that isn't all that similar to any of the individual or any of the components that make up that make it. So that sort of thing, there's a family of things called vector symbolic architectures that have been explored for doing math like this. Whole bunch of different approaches. They all have this idea of there's some sort of addition, there's some sort of binding operation, there's some sort of unbinding operation. The particular one that we're going to use was called holographic reduced representations. It was developed by Tony Plate in the late 90s. And it's got that same form. The particular operations that he's using are vector addition, circular convolution is the binding operation, and circular correlation is the unbinding operation, which is the same as circular correlation also is circular convolution with a vector inverse. And the so like that, Tony Plate had done a bunch of research using this particular representation, showing that it's kind of nifty for doing symbol-like manipulations. But it's using these weird operations, circular convolution and circular correlation, which seemed a little strange at the time. when we sort of, or I guess when in the context of the neural engineering framework stuff, this actually jumps out really as a really promising idea, because those operations, vector addition and circular convolution, circular correlation, are exactly the thing that neurons are good at. Vector addition is that is a linear, completely linear. Yay, neurons are good at approximating linear functions. Circular convolution just requires a bunch of pairwise multiplies. And so that's all of those operations are extremely well approximated by low degree polynomials. Right? So the vector addition, that's degree 1 polynomials, circular convolution and circular correlation, that's degree 2 polynomials. Right? This is beautiful. Okay. Surprising, but cool. And so if you go ahead and do that, you get now you can sort of say, okay, well, this is the math that we're going to do. Now you can build neural networks that do that binding, do that comparison, do that storing. And with that same question that we went to before is, okay, well, what if you have that 700 dimensions and 40,000 neurons that I was talking about before? And then you decide, okay, I'm going to have 8 pairs of items. So, that's a total of 16 terms, all bound in pairs of 2. And add those results all together, shove that vector in to one of these groups of neurons and see what you get out. And then is that result the closest, is that result closer to the correct answer you put in than anything else? If you just randomly generate all of those vectors and sort of just do that math and find out, then yes, it will do that task with about 95% accuracy using 40,000 neurons. Interestingly, if you drop the number of dimensions, it gets bad pretty quick. So, or what do I want to say there? It's much better with more dimensions, right? So if you're running with 32 dimensions or 64 dimensions, this sort of thing just doesn't behave well at all. It sort of just barely works. You really want to be up to sort of 128, 256 dimensions at the bare minimum. But then you get this beautiful exponential growth that gives you tons and tons of space. And there's some slight speculation that this becomes an interesting question about do we want to sort of, when modeling human cognition versus, say, other mammal cognition, is there something we could say about, hey, one big difference is scaling this number of dimensions? That's a very speculative statement I just made there, but it's at least a possibility. Okay. So what am I saying here? Groups of neurons can store vectors. Fine, we knew that from before. This cool thing we've got presented here is this vectors can represent structured information by using this binding sort of operation. The accuracy of that representation is limited by the number of terms in the language, the number of items we've combined together, the level of nesting, because when you do this binding, there's no reason why you can't just take another big combination of things and multiply that in. Right? You can nest parentheses, it's no problem. So you can use this to represent symbol trees. So you can do all that, and as you scale that up to something like the upper limit of what you want to be able to, what you might be able to argue you see in human cortex in terms of groups of neurons that are all connected together, or majoritarily connected together. Yes, it will scale up. You can do this with about 700 dimensions. That gives us an upper bound as to what we should be doing. And so let's give that a try. So again, we're going to go back to Nengo. We're going to go to the built-in examples tutorial, and we'll do the we'll do the unbinding, because that's got both the binding and the unbinding. All right. So what have we got here? Similar to what we had before, but I've got 2 inputs. I've got shape and color. Okay, and I'm going to be feeding those into a memory. Let's focus on that part first. Okay. And we've asked the system already to be set up such that memory is color combined with shape. Okay. And again, it's all this is just a syntactic shortcut for defining exactly the math that I was just saying. And so let's give this a try. All right, so if I run this, okay, first of all, it's going to take a little bit longer to start up, because we're starting to get to a fairly large model now. There we are. So if I take this system here, and I right-click on here, and I say, all right, the shape is a circle. Okay. And the color is red. Now, when I started the simulation, it did not know any of these vectors. We are randomly generating new vectors right now. I can feed in, I've got circle and red. Okay. I'm feeding in some vector that means circle. I'm feeding in some vector that means red. The neurons are computing the circular convolution of those two. And we have that result sitting here in memory. You will, just as a user interface issue, you will notice the memory now is saying circle red as an option. This is actually a user interface option. So if you say hide pairs, then it's only going to be comparing the vector that's in this memory to the basic terms that it knows. And the result is, I guess it seems like a little bit close to circle, but that's just random. Just because, hey, there's only two words that it knows, and so it's not all that surprising that the vector that's in memory is vaguely close to one of them. So we do want to make sure that we have show pairs turned on. So that way it's saying, okay, yeah, it was kind of close to circle, but it's really close to the correct mathematical answer of multiply circle by red, or do the circular convolution of circle and red. And now to show that we can do queries on that memory, because if we want to say, okay, is this a representation of red circle, I need to be able to say, all right, what color is the circle? So I'm going to feed in a query that is red, and I get out the answer circle. Okay, and that's because we've also told it, hey, set things up such that we take memory, whatever's in memory, combine it with the inverse of the query, and the result goes into the answer. Okay. Again, this is just the syntactic trigger that we've made, or that we've developed. We've been in order to make it faster to define these sorts of models. Okay, so we can ask we can query it with red, we get out circle. I can query it with circle, I should get out red. I query it with something that's not in the memory, I query it with blue, I get noise out. Something's just, not all that close to anything. So that's saying that I can store red circle. How am I? All right. I can also feed in something else, because again, when we started running this model, all of these vectors had not been defined yet. It's just made to just do the math in general. So if I go, I don't know, square and blue. Okay, so now we're going to have a blue square in memory. All right, so that's in memory. Let's actually because this is set up as a memory as an integrator, let's go ahead and take away that input. Okay, I can take away that input. I've got blue square in memory. I can query that memory. Blue, feed in blue, I get out square. I feed in square, I get out blue. Okay, so that memory is working as before. If I wait long enough, this will drift and disappear from memory. But let's do one more thing first, because this memory has currently got blue square in it. I'm going to pause my simulation. I'm going to feed in red. Whoops, that's the wrong thing. I want to feed in square and feed in red. My memory has red square in it. Let's take away that input. And that was too quick, it looks like. Still have blue square. Oops, actually. Let's go with square, red. I want to feed in red square. Good, we've got red square in memory, that's what I wanted. Circle and blue. There we are. Sorry, this is what I want. So I've got red square in memory, I've got blue circle in memory. Now I'm going to take these inputs away. I have both things in memory now. I have red square and blue circle, or at least I have a vector in memory that is fairly close to red square. It is also fairly close to blue circle. Now I can do queries like, what is blue? I get out circle. Red, I get out square, kind of close to square. The fact that it's also a little bit close, kind of close to red, is partly, yeah, sort of. There's no particular reason why it happens to be close to red. I would say that's just random noise in it's randomly generating these vectors. As you scale up the number of dimensions, that sort of coincidence will happen less often. I mean, we're using 32 dimensions here, which is sort of bare minimum. Feed in circle, I get blue. Feed in blue, I should get out circle. Yep. Of course, as I scale up the number of dimensions, the simulation is going to run slower on your computer. That said, 64 dimensions you should be able to get away with on a reasonable laptop. And if I want to scale this up to human-sized vocabulary, about 700 dimensions is about where I would put it. We tend to actually use 512 dimensions. That's also pretty close. All right, but the point of all of that is this is a general method for solving the binding problem, for being able to encode symbol structures in a vector and perform manipulations on it. And the new, I mean, that's been known for a while. These vector symbolic architecture people have studied this sort of thing for a while. The new thing that is here is, hey, look, all of these components, all of these steps we can do in neurons and keep things within the constraints that you see in human cortex, which is pretty cool. All right, so that's the general approach for representing symbols. You can use that to do pretty much all the symbol manipulation, general symbol manipulation type tasks that we're familiar with. But let's go a little bit farther. Let's go one step farther in that if this turned out to just sort of be a mirror implementation, like just do exactly the same thing as normal symbol manipulation, but it's just kind of noisy, that wouldn't be as exciting. What I'd really like is, are there new capabilities here? Because we've been forced in this domain. And the answer, of course, is going to be yes. And that's going to be fundamental to how we do this particular task here. And I would like this as just an example of why algorithms look incredibly different once you're forced to do something weird like, okay, everything has to be vectors. So the task you just saw was the Raven's progressive matrices task that we showed earlier. There's a pattern. 555 is what comes next. How are you going to do that? Like forget implementing that in neurons. What algorithm are you possibly going to come up with that would make that system work? Right? People have modeled Raven's progressive matrices tests in a bunch of different ways in the past, and it's hard. It's hard to come up with what sort of algorithm would do this. So how did we do it here? Well, first of all, we've got each of these different, all these different squares that were presented, so the different things we're making the pattern up out of. So each of those, we can sort of see, okay, I could represent each of these components. Right? So we have each of these components, and so this, if I wanted to represent the pattern in one of these components, there's a bunch of different ways I could do it. Here's what turns out to be a pretty good way. I'm going to have a vector for each number, and I'm also going to have a vector for each position. And then if I want to represent the first thing, it's a 1 in position 1. So that's the first square. And the second square is a 1 in position 1 and a 1 in position 2. Right? And the third square is 1 in position 1, and so on. Okay. It's an interesting challenge to sort of, to how do you build up that vector using just the visually presented input. And that's going to involve a lot of the cognitive control stuff that we'll talk about in the next lecture. But each of the individual steps, I hope you can see that all we need to do is be able to compute the binding operation. And we just ran a model that can do the binding operation. And for addition, that's just, all right, feed things into the same network and integrate, and you will get something like addition. Or feed them in two separate components and feed them into the same group of neurons, and you'll get addition. So hopefully you can see that each of these components is something you can build using stuff we've seen so far. So that's all just vectors that we can build up. And so we have all of these vectors that represent each of these different blocks. So each of these is a vector. So what can we do with that? Well, since they're just vectors, so each of these is a vector that represents a symbol structure, fine. But since they're just vectors, I could also do something like, okay, well, what is the vector that if I bound it with one of these, I'd get the next one? So in particular, so this pair from S1 to S2, I can just do the math of, all right, if I take the inverse of this and bind it with this, then that will give me what is the vector that if I bound it with the first one, I'd get the second one. Okay. And then I can do that. So this math gives me a new vector, and that vector is the vector that represents the transformation between two symbol structures. Okay, that's kind of weird. But I can do that to the next pair as well, and the next pair, and the next pair, and the next pair. So I've got 5 different vectors, each of which represent mappings between symbol structures. Cool. What else can I do with that? Well, since they're all just vectors, I can average them together. Right? So now I have a new vector, and that vector is the average transformation between a bunch of pairs of symbol structures. It's a weird thing to represent. But then it turns out that if you take that resulting vector and you bind it to this, you get a vector that is pretty close to the correct answer. Okay, it's approximate, and it is it's closer to the correct answer than any other interpretation. So, but that is a very odd way of doing this particular pattern completion task, and it's something that is only natural to do once you've been forced into this domain of vectors. Okay. So again, that's my key point there, is once you're forced to do vectors, weird alternate new algorithms start to come up. The fact that you can treat these things both as symbols or as something symbol-like and as vectors seems to give a whole bunch of new possibilities for algorithms to explore. That's the fanciest algorithm that we did in Spawn in terms of complicated symbol structures. We set the system up to do 8 different tasks, and it switched between tasks just simply based on its visual input. The visual input would tell it, so the beginning of the visual input would tell it, okay, what task are you doing now? And it is possible, all of these things are now things that you can build up using this approach. Cool. Summary of all of that. Yes, groups of neurons can store vectors, and vectors can represent structured information. We've got some limitations on the accuracy. This idea of these semantic pointers, these vectors that are sort of compressed representations of all sorts of symbolic information. All the examples I've shown so far is we're just combining together symbol stuff, but it also works for any vectors. You can also combine sensory information. You can, so like one of the things being bound in could be, a compressed version of the visual image. There is some interesting questions about why you might want to do, like, why would, why is this binding together useful? Why not just have separate groups of neurons for each of these different things? I think there's a bunch of interesting aspects of, yes, if you're going to be passing information from one brain area to another, you want to be able to sort of minimize the amount of information that you're passing around, less information to store in long-term memory. There's also this interesting aspect that with these representations, the same way in the first class, if we were trying to represent the product of two values, we needed to make one group of neurons that represented both of those pieces of information. Something similar might be happening here, that if you're doing nonlinear operations on your symbol structures, then you want to have them all represented in one vector. Cool. We'll leave on that. Neurons can represent vectors and functions on vectors. This has sort of suggested this particular somewhat non-standard approach to representing concepts and combinations of concepts. And we can encode that as a single stored representation. That's the approach that we're taking for doing a sort of higher level cognition. I don't think it's the only technique possible. It's the only one we've managed to get working. There's other possibilities of maybe how people might want to try to represent simple structures. We have not been able to get other ways to work. This is what we focused on. And then we've sort of having fun. Let's map this whole process onto different brain areas, constrain things with different neurons. Of course, the models we built so far are pretty limited. We've only implemented a few different brain areas, and there's still tons of research to be done to try to improve that and set up the organization of the model better, or how do you organize all of this information to make it look like the brain? How do you control the information flowing between different areas? Those are going to be big important things that'll happen next. So we will talk about that in future lectures as we start getting into this question of how do you coordinate all of the interactions so that we can build each of these individual components. How do we coordinate it all together to work as something like a cognitive architecture itself? Okay. Thank you.